Here is the key for quiz 5. Another roadmap problem. We are asked to fill in the boxes here as we go from the 1-pentene to this much more fancier aromatic substituted compound. So in order to get to this primary alcohol from 1-pentene, we need my favorite reaction, BH3THF, followed by base and peroxide. And that is from first semester organic chemistry. Then PCC plus a primary alcohol gives us the oxidized product, an aldehyde in this case. And then I want to take this 5-carbon aldehyde. Looks like I have 5 carbons right here. So I need to add this aromatic ring and end up with a secondary alcohol. So I need a phenyl Grignard. That's step 1. Step 2 is mild acid workup. And then I have a number of boxes that are empty. I take this secondary alcohol with a phenyl ring on one side. I turn it into a ketone with a bromine on the phenyl ring. So what I need to do is somehow change this substituent into a meta-director and then install the bromine. And if I change it into a ketone, as we see here, we know that that is a meta-director. So I should oxidize it first. I can probably just use PCC again for that. Now I have a acyl benzene ring, and I can add bromine in the meta position with Br2 and FeBr3, and then I have my desired product. Question 2. This asks again about acidity, and so we're going to look at these alcohols in terms of their acidity. There is no resonance stability available for any of the alkoxides that might be formed on any of these, so resonance is not going to play a role. We do see a difference in steric bulk between the middle one and the two outside, and I see some inductive effects from these chlorines here. So the one with inductive effects should have the most acidic hydrogen, OH group, and the most bulky OH should be the least acidic. Again, because when we form this compound, we get a bulky alkoxide. It's harder to stabilize that via solvation with this large bulk. And that would give 2 for this propanol. All right, for 3, we're asked to fill in reagents or starting materials for these incomplete reactions. Here we're taking a alkyl group, turning it into a carboxylic acid, and we can do that with the sodium dichromate oxidizing reagent, Na2Cr2O7. For B, we're asked to take this primary alcohol and turn it into a carboxylic acid. We can do that also with chromium reagents. Let's use Jones reagent in this case, H2CrO4, mixed with water. That will give us a primary alcohol oxidized to a carboxylic acid. And the second one here is, looks like we need to fill in the starting material. We're reacting a ethyl Grignard followed by mild acid to make this secondary alcohol. We know that Grignards can make alcohols, so we either make this bond or this bond. And since right here is a 2-carbon species, I'm going to say that we should have started with a 4-carbon aldehyde. React that with the Grignard. And lastly, we are asked to come up with the starting material, react sodium borohydride and ethanol to make this secondary alcohol. And we know that this is a reducing agent that provides H- to take carbonyls to alcohols. So in fact, we should have added the hydrogen that is not drawn right at this position. So let's redraw the starting material without a hydrogen at that position and a double bond. And so that would be the starting material I'd expect for that reaction. Moving on to number 4. We're asked for a reasonable arrow-pushing mechanism for this reaction, and we are given 2 equivalents of methyl Grignard and 2 equivalents of mild acid workup then at the end. And this is a lactone, but more generically it's an ester. We know that Grignards add to esters, so let me draw my Grignard a little bit more carefully. This is simply a Grignard addition to an ester. And then the second step is loss of the OR group. And here we're not really losing it because it's still attached. And now I have a ketone I can add my second Grignard to. And I end up with 2 alkoxides now. And I can proton transfer or protonate both of those. So let's get H3O plus in here. I'm going to show them one at a time. There's my first, and then here's the second proton transfer to get to the product. And you can straighten out the chain and you'll get the straight chain version right here. Here is quiz 6. We're asked to match each of these 3 spectra with one of the following compounds, and I'm going to just label the spectra A, B, and C so we can keep track of them. So these are our choices, and each one of these spectra will correspond to one of those choices. So let's look at the first one. This is a Proton Nmr Spectrum. We know that because it goes from 0 to 8 ppm. We see that there are 3 signals here, a 3-hydrogen triplet, a 3-hydrogen singlet, and a 2-hydrogen quartet. And you can see that they're, some of the signals have been blown up so that we can more clearly see their splitting pattern. And we know that the 3-hydrogen triplet is a methyl group, and because it's a triplet, we know it's attached to 2 other hydrogens. So these 3 hydrogens correspond to that triplet. And then we can find that these 2 hydrogens correspond to that quartet because they are attached to 3 other hydrogens. And we know that this is attached to some X group that does not have any hydrogens attached. And that leaves us with the 3-hydrogen singlet at about 2.15 ppm. So chances are that is a methyl next to a ketone. And that is probably what we're looking for here. Do we see anything that has an ethyl and then a methyl next to a ketone? There's a methyl next to a ketone right here, and that's really the only one that's going to work. Here we see an ethyl group. We've got evidence for the ethyl group, and we've got evidence that this CH2 is attached to a carbonyl because it is shifted about 1 ppm more than its base shift. So I'm pretty sure that A is this butanone molecule. Let's look at B. B, again, is a Proton Nmr spectrum. It only has 2 signals, a 6-hydrogen doublet, and it's very hard to see that there are 2 peaks here, so you can see that whoever made this put a doublet there for you so that you can more easily interpret the spectrum. And then this lump of peaks right here integrates to 1 hydrogen, and it is a septet. So we know that the 6-hydrogen doublet is probably 2 methyl groups that are the same. They're equivalent by symmetry. They're adjacent to 1 hydrogen. So each of these methyl groups that I've just drawn is a doublet because this hydrogen splits them into 2. And this makes sense because this H we'd expect to be a septet because it is adjacent to 6 hydrogens. And indeed, we are told that it is a septet. If we blew this up, we probably could see that it is a septet. And we see that the septet is shifted to about 4.3 ppm instead of 1.7, so that is approximately 2.6 ppm extra. So most likely X, maybe that's an O, or a strong electron withdrawing group. So I'm going to look for a compound that has this arrangement. This is called an isopropyl. I could also draw this without any hydrogens attached, and these would be the same thing. So I'm going to look for an isopropyl group attached to a strongly electron withdrawing group, and I see this, the carbonyl does not have quite the effect of a 2.5 ppm shift. This I might expect to be 1.7 plus 1 is around 2.7, That's clearly not even close to 4.3. But we do have an isopropyl there. There's no isopropyl. Here's an isopropyl. This is also an isopropyl, but this T-butyl group attached to it is not electron withdrawing in the least. So the likely candidate is isopropyl bromide. Bromine is a strongly electron withdrawing atom, and so it is likely that it has a pretty good chemical shift of the CH that's right here. And so I think that isopropyl bromide is the best choice for this spectrum. Let's look at spectrum C. It's again a Proton Nmr spectrum. However, in this case, it is just from about 1.5 to 4 ppm, so we can assume there's nothing in the 4 to 10 region, otherwise we would have shown that to you. There's no reason to try to trick anybody while doing these problems. So let's look at these 4 peaks. We have 4 types of hydrogens present, and the signal at 1.9 ppm looks like it has 5 signals in it. So this is a 2-hydrogen pentet, which means I have 2 hydrogens that are next to 4 hydrogens. So one possibility would be a CH2 that is next to 2 CH2s. Another possibility would be a CH2 that's next to a CH3 and a CH. Generally, this is going to be more common, especially when we have a nice pattern here that looks pretty uniform. This pattern is symmetrical and pretty uniform, so most likely I have a CH2 that's in the middle of a chain of CH2s. If I look over here, I've got 2 hydrogen triplets, which is what I would expect if these 2 CH2s were not the same and also not attached to anything else that bears hydrogen. So maybe they have, let me erase this star, it's getting in the way here. So maybe we have 2 X groups here, and both of these X groups do not have any hydrogens on them. In that case, I'd expect a CH2, such as this one, to be a 2-hydrogen triplet. And I'd also expect that of this CH2 as well. And if X is not the same, these CH2s would not be the same, and so they would have slightly different chemical shifts, or even more drastically different chemical shifts. So I'm going to look for, in my molecules up here, anything that has 3 CH2s in a row, and it's pretty easy to come upon this molecule as one possibility. It's the only one that has 3 CH2s in a row. This 1-hydrogen singlet right here at about 3.8 could certainly come from this OH. So I'm pretty sure that what I have is this molecule for part C. On to quiz 7. We're given a Proton Nmr spectrum. We are told that there's a strong absorbance in the IR spectrum at 1688. That's a pretty good indication that we might have a CO double bond. There's nothing above 3100, which tells me there's no alcohol. What else can we look at here? The carbon-13 NMR spectrum has 7 total peaks, so I have 7 types of carbons. 4 of them are between 120 and 130. That's probably an aromatic ring. And 1 is at 200 ppm. That is probably a carbonyl, which I already suspected because of the IR data. So let's look at the Proton NMR now. There are 5 hydrogens in this lump here, 2 lumps in fact, and so most likely that is an aromatic ring with 1 substituent. Sometimes we're not going to be able to decipher the shape of the peaks in the aromatic ring. Really the only useful information we can get is the fact that there are 5 hydrogens, or maybe 4 hydrogens if we have 2 substituents on the ring. Also, we have a 3-hydrogen triplet at about 1.2, a 2-hydrogen quartet at about 3, and this is very indicative of some sort of ethyl group. The 3 hydrogens in this methyl should be split into a triplet because they are next to the CH2. The 2 hydrogens in this CH2 should be split into a quartet because they are next to the 3 hydrogens in the methyl group. So let's go on and look at some more of the questions here. What can I conclude from the NMR signal at 3 ppm? This is a CH2 next to CH3. And I know that the base shift of a CH2 is 1.2, and if I add 1.8, I can get to 3.0. So I do have some effect of a nearby electron withdrawing group. Perhaps the aromatic ring is affecting it somehow, but that is something to keep in mind, that it is attached to something that's not just a standard carbon. It also is attached to something that has no other hydrogens, again, because it's split into 3 and we know that it's attached to the methyl. What can I conclude from the IR? There's a carbonyl, no alcohol. We concluded that there was an aromatic ring and also that there was a carbonyl from the carbon-13 data, and propose a structure that fits all the data. The only thing I didn't draw on this chart was the carbonyl. That's all the information I have. So the only way to put those together, of course, is like this. So that seems like a reasonable structure for this molecule. All right, on to question 2. We are given a proton NMR, a carbon NMR, and a mass spectrum. And again, this is being recorded in spring of 2018. So in this class, this semester, we did not use mass spectra. So I'm going to say the information we got from the mass spectrum was basically the formula. C4, H7, O2, Br. So we analyzed the mass spectrum, and that is the formula we obtained. So let's go ahead and look at the proton NMR spectrum. We have 3 different signals. They do add up to 7 hydrogens. So that confirms the 7 hydrogens there. These 2 signals, 2 hydrogen triplets, are very likely coupled to each other because they are the only splitting patterns that we observe on this spectrum. So probably we have a part structure that looks like that, where X does not have any hydrogens attached because each of these CH2s is a triplet because it's adjacent to the other CH2. And then we have this 3 hydrogen singlet, which is very likely a methyl group. And because it is shifted so far towards 4, it's at 3.7, most likely it is attached to an electron withdrawing group. The options are bromine or oxygen. If I had a bromine here, I hope you'll agree that my molecule is complete. There is no more attachment points that I could fix on this molecule. I have bromomethane, so I don't think that's going to work. I think we have OCH3, so that has an attachment point. Let me erase this other one so it doesn't get in our way. So those are that's the information that we can generate from the proton NMR spectrum. Another thing when we have the formula is to calculate HDI, so let's go ahead and do that. That's 4 times 2 plus 2 minus 7 hydrogens minus 1 bromine, all divided by 2. And that equals 8 plus 2 is 10, minus 8 is 2. 2 over 2 is 1. So I have a ring or a double bond. I'm going to guess that I do not have a CC double bond because all of my hydrogens are accounted for. And if I had any hydrogens off of that CC double bond, they would appear way up near 5, 6, or even 7 ppm, and I don't see any of that. I have this small proton NMR spectrum. It is safe to assume there is nothing hidden on the greater than 4 ppm section or the less than 2 ppm section. I am not going to give you half a spectrum and expect you to come up with the other half. That would not be fair, and there's just no reason to do that. So we can assume there is no hydrogens attached to alkenes, and that tells us, that doesn't prove that there's no alkenes, but it helps us conclude that there probably aren't any alkenes. We can also conclude that there are no alkenes by looking on the carbon spectrum from 100 to 150, and we see nothing there. And so that means we probably don't have an alkene either. This is a carbonyl peak at about 170, and you'll notice that I annotated it to say that there's 1 peak there. It does look like 2, but it is in fact only 1. So I have another part structure that I can put here, the carbonyl. And then the last part structure, of course, is the bromine. And so we'll notice there are 4 part structures. 2 of them have to go on the end of a molecule or the end of a chain because the bromine only attaches in one spot. The methoxy only attaches in one spot. So these 2 are in the middle. So I can automatically just add them together. So now I have something that looks like that. And the choices are, where does the bromine go? It could go on the end without the carbonyl. The methoxy would then go right here. Or I could put it next to the carbonyl. And in this case, we really don't have enough information to argue against either of these or support one over the other. I can tell you, though, that it's much more likely that it is this structure. And that's because the bromine attached to a carbonyl would be called a carboxylic acid bromide. It's highly reactive, very unusual to see one of these in sophomore organic chemistry, and even more unusual to see one as the subject of a structure-solving problem such as the one we're working on right now. So it's very, very unlikely that you'll ever see a bromine directly attached to a carbonyl, especially in a structure-solving project like this. In Chapter 21, the carboxylic acid derivative chapter, we will see something like this. Acid chlorides attached to, chlorides attached to carbonyls. That is a perfectly valid molecule. We're just not going to study that by NMR very often. So if you're faced with the choice, as I said here, A versus B, A is just much more likely if you don't have anything else to go on. So in this case, I probably would have given just about all credit to anybody who came up with either A or B, but in fact the answer is A in this case.